Is recording. Okay. Hello, I am Walter Faria. I'm a PhD student at Física under the supervision of Professor André de Camargo. I'm in my fourth semester, so I've started my PhD in March 2019. And I'm here to present my work, The Effect of Tungsten Oxide Content in Phosphate Glasses on the Energy Transfer Process between Trivalent Rare Earth Dopant Ions. So we'll be studying phosphate glasses containing sodium phosphate, tungsten oxide, europium oxide, and terbium oxide. We'll be increasing tungsten oxide while decreasing sodium phosphate, and check the effect of this increase of tungsten oxide. And why is that? What will be the effect? Well, this oxide possesses a really high polarizability. And polarizability affects the intensity of rare earth transitions. So as the polarizability increases, as we might expect from the tungsten oxide, we might see an increase in the intensities of the rare earths. On the other hand, we are not expecting any energy transfer process difference due to this polarizability. And why is that? So there are two main mechanisms that give rise to these transitions in rare earth ions. And one of them that depends on polarizability, it's not present in energy transfer. So that's why we're studying this. Our aim is to differentiate between these two mechanisms that in principle they are not able to be separated, but looking at the intensities that depend on both mechanisms and the energy transfer process that depends on only one mechanism, we might differentiate between them. So what are these mechanisms? Okay, so this is the transition rate in an intensity in a rare earth transition, right? So there is the wave number. There is the matrix element that connects both the initial to the connects the initial level to the final level of the transition. This only depends on the levels. And there is this so-called intensity parameter. And this parameter here depends on these two mechanisms that I'm going to talk about. These parameters depend on the environment, the symmetry around the ion, the degree of covalency bond of the ion, and of course the polarizability. So what are these two mechanisms? They are the induced electric dipole. This is exactly like a regular electric dipole, but is induced because in principle the pure electric dipole transition is not allowed in rare earth ions. And the other mechanism is the dynamical coupling. This dynamical coupling arises when incident light, incident photons create some kind of oscillating dipole in the surrounding atoms around the rare earth ion. So these oscillating dipoles caused by the incident light give rise or can increase the transitions of rare earths. And that's where polarizability enters. So a higher polarizability, so you create more easily these oscillating dipoles, and then the transition becomes stronger. So in the absorption graphs here, we can see some transitions of europium and terbium. They're not important here, but we can see clearly that the glass are transparent, almost no absorption at all in the visible range, only for the 40% tungsten glass, where we have an absorption of the tungsten 5 plus species. This species occurs as more tungsten is added to the matrix. So the 40% glass, because of this band, it's kind of blue, but all the others are really transparent. And how we can calculate the polarizability, or at least get a general idea about it. We can look at the energy gap. So the polarizability depends on the energy gap like this. So if the energy gap decreases, the polarizability increases. And we can calculate the energy gap through the talk plots that we see here. So we can clearly see that the 5% glass has a higher energy gap than the 40% glass. And this is what it's shown here. So the energy gap is decreasing. So if it is decreasing, we can expect an increase in the polarizability. Other things that increase with the addition of tungsten is the density. The glasses become denser, and the molar mass. Another way to calculate polarizability is through the optical glass basicity. Basicity is nothing more than the average electron donor power of your matrix. So as basicity increases, the polarizability will also increase. We can calculate basicity from glass composition. That's what we've done here. So it is increasing. And through this equation, we can see the polarizability also increases. So we know for sure when we move on from 5% tungsten to 40% tungsten, that the polarizability increases. So we might expect an increase in the intensities of these ions. That's exactly what we see here. So from 570 on here, we have the europium emissions. This graph here is normalized by this band around 590, and we can see clearly an increase here in this band around 60-15 nanometers. In the set here, we have the integrated areas, so we can see even more clearly how much this transition here increases. And this spectrum is normalized by this band because this band is not does not arise from induced electric dipole or dynamic coupling. It arises from magnetic dipole transitions. This is a transition through magnetic dipole. So this transition does not depend on polarizability or symmetry or whatever. It only depends on the final and initial levels. So, and the refractive index also. So this transition always has the same intensity. That's why we normalized by this band here. And through this normalization, through the ratio between this band that only depends on the omega-2 parameter, the ratio of this band to the constant band, let's call it this way, the magnetic dipole band, we can calculate the omega-2 parameter. And we can see, of course, since this emission here increases, the omega parameter increases a lot. So here we can see also the effect of polarizability, but not only on the intensity parameter. So again, we know for sure that the polarizability of these glasses are increasing. But these emissions here from terbium, they are actually decreasing. But this is not related to the intensity parameters. This is because the transition from terbium to europium increases with increase of tungsten. The gap between the levels that are involved in this energy transfer between terbium and europium are separated by more or less 950 inverse centimeters. Right. So if we have a phonon in our matrix that is close to it, this phonon bridges this gap, and then the transfer occurs. And we have this kind of phonon. Is this 915 inverse centimeters phonon here that we can see in the phonon side bands that appear in the excitation spectrum of europium. And as we increase tungsten, this funnel, this exactly funnel that we need to bridge the gap between the levels involved in the energy transfer, the contribution of this funnel increases as we move on from 5% tungsten to 40% tungsten. The contribution to the whole of the funnels here, I've calculated the relative area, and you can see going from 17% to almost 40%. So it means that more phonons of this energy are available, so it's much easier to transfer energy from terbium to europium via this energy gap here. And this is why, as we increase tungsten, the emissions from terbium decrease because they are being transferred, their energy of the emitting levels are being transferred to europium ions. So we say that both the intensities of the transitions are increasing and the rate of the transfer is increasing. So we might check this energy transfer mechanism through the lifetimes. Okay, the mechanism of the emissions are like this. We are exciting terbium, it relaxes to this level here, and then terbium might emit, as we saw in the other graph, but it also might transfer energy to this other level of europium, and then we see emissions from europium. This gap here is bridged by that funnel that I showed you in the previous slide. Okay, we can calculate the energy transfer rate through the comparison of the lifetimes of both the co-doped sample and the terbium only sample, and then the difference between the emission between the excited state lifetimes will give us the energy transfer rate. We can see the lifetimes are always decreasing as we increase tungsten, but when europium is present, lifetime also decreases as we might expect, because some of the ions in this level here are losing energy to nearby europium ions. So through this equation here, we can calculate it, and we see in the black points here how the transfer rate increases, but it's just a little bit. We can see better here in the table. It almost doubles, and it's still really, really low. The strongest, the highest transfer rate is around 60, so it's really, really low. And we can say that this transfer increases is not due to the polarizability that increases a lot. So we would expect a much higher increase in the transfer rates. This increase is only due to the funnels, as we showed previously, and also because since the glasses with more tungsten are denser, so the rare earth ions are closer to each other, so their distance are lower, and then the transfer rates will be also a little bit higher because of this closer distance. So these are the things that cause a little bit of the transfer rate increase, not the really high polarizability increase, right? We can check that by looking at the transfer efficiency through this equation here, also comparing both lifetimes. And we can see the transfer efficiency almost does not vary, okay? So from 7% to 10%. So it's basically constant. So if the higher polarizability would increase the transfer rates a lot, of course, for 40% tungsten, we will have a much higher transfer efficiency. And this is not what we see here. So we can clearly see that although the polarizability in our glasses increase, the transfer rates do not increase substantially. So we can, from now on, try to model all these transfer rates using the calculated intensity parameters that contains both dynamic and induced coupling, but this will be wrong, will be different from the actual measured rates, because they only account for the induced electric dipole. And then from this difference, we might actually calculate the contribution of dynamic coupling to the intensities of the transitions in rare earth ions. Okay, so I want to thank all the funding agencies, the ones that pay for the equipment in the lab, for the reagents, and also CAPES that pays for my scholarship. So thank you for your attention. Goodbye.